Our discussion of nuclear reactions begins with this topic of radioactivity. Now, radioactivity was discovered around the beginning of the 1900s, primarily by this person, Becquerel. But a lot of the more famous studies were done by Pierre and Marie Curie, who have become very famous for their studies on radioactivity. Now, what we mean by radioactivity is that certain nuclei of especially larger atoms, they spontaneously emit particles or energy from the unstable nucleus. Now, there are three different types of particles or energies that are released through radioactivity. You can have an alpha particle, you can have a beta particle, or you can have a gamma ray. Let's take a look at this picture here on the right of your screen. You can see there is a green substance, a radioactive source, that's contained in a lead container, which has an opening just at the top. What this does is it blocks the alpha, beta, and gamma particles from going in any direction except for up. That's it. So the lead container is very good at absorbing or blocking all of these different particles. That's why when you go to a dentist, for instance, they put a lead vest on top of you so that when they give you x-rays, you are protected, because lead is a very good protector from high energy radiation. Now, let's talk briefly about the difference between these three particles. Early research showed that the basic difference between these three particles was the charge. For instance, if you were to have this radioactive emission pass through a magnet, then it would turn out that the alpha particles would turn one direction, the beta particles would turn another direction, and the gamma rays would go straight. When the alpha particle turned one direction, that would tell us that an alpha particle is positively charged. But the beta particle, which turned the other direction, is opposite, so negatively charged. And the gamma ray, since it passes straight, undeflected, that indicates that it is neutrally charged. We'll talk a little bit more about what each of these three things is in just a couple slides. But first, I need to make a very important distinction between radiation and radioactivity. These are often confused together in our society and considered to be the same, but they are not the same. They are very, very different. Radiation, as we've discussed back in Chapter 7, talking about light, radiation is an electromagnetic wave, a wave of electric and magnetic fields. Some examples of that would be light, radio, microwaves, infrared, television, X-rays. There are a whole variety of waves of radiation, most of which are good and very important in our lives. Radioactivity, on the other hand, is the spontaneous emission of particles or energy from an unstable nucleus. And only sometimes is this radioactivity the emission of high energy radiation. As we saw, there were alpha particles, beta particles, and gamma rays. Only gamma rays are high energy radiation. And it's only the high energy radiation. We're not talking about emitting a radio wave or something like that. Okay, so before we can finish talking about radioactivity, let's remember a few fundamentals about notation for nuclear equations. Remember that the atomic number is the number of protons in a nucleus. So here on the left, recall this figure, we have three different types of hydrogen, three different isotopes. Remember, an isotope is where you have the same atomic number but a different number of neutrons. The atomic number for all three of these types of hydrogen is 1, because there is always one proton in each of these three types of hydrogen isotopes. The mass number is the total number of nucleons, that is, protons plus neutrons that are within the nucleus. So in hydrogen 1, you have 1 proton, 0 neutrons. The mass number is 1. That's indicated by this upper number in this notation. Hydrogen 2 has a mass number of 2 because there's 1 proton plus 1 neutron. And so we indicate that isotope as 2. Hydrogen 3 has 1 proton, 2 neutrons, so the mass number is 1 plus 2, or 3. Now, we can do, knowing this, we need to, as we do nuclear reactions, we have to include atomic numbers and mass numbers. So that's very important when we balance equations. Not only when we do deal with nuclear reactions, we're not dealing with the same atoms from the reactant side to the product side like we did back in chapter 10. This time, we are balancing the number of protons and neutrons. First of all, your charge has to be conserved. So remember here in this table we have we're describing the charge and mass numbers of all the particles we need to worry about in nuclear reactions. We have protons, which have a mass of 1 and a charge of positive 1. Electrons, which are far lighter than protons, and so we say it has a mass number of 0, but it has a charge of negative 1. We have neutrons, which is about the same as a proton, so has a mass number of 1, but a charge of 0. And then gamma rays has no mass, has no charge, so both of those are 0. So those are some common symbols you'll see. So when we deal with nuclear reactions, we have to conserve charge and we have to conserve the mass number. By conserving the charge, we need to look at the atomic numbers. So for instance here, we have uranium, which is undergoing alpha decay, which is, you start off with uranium, you take enough protons and neutrons out to make the nucleus of a helium atom, and then whatever's left remains. So for instance, we start off with uranium, which is element 2. Helium has 2 protons, so a charge of plus 2. Whatever's left is the remaining atom. And so it would be element number 90, which if you look at a periodic table would be thorium. So uranium, by losing 2 protons, has become thorium. That is our charge conservation. You have a total charge of 92 on the left with uranium, total charge of 92 on the right with thorium plus helium. Now we have to conserve the mass number. In other words, the number of protons and neutrons has to remain the same as well. So we started off with 238 protons plus neutrons, or 238 nucleons. We have to have the same mass at the end. A helium nucleus, or alpha particle, has a mass number of 4, 2 protons plus 2 neutrons. So what's left is 238 minus 4 is 234. The thorium has a mass of 234. All right, now here's a very important point. This is very critical when we talk about the protons in a nucleus. If you think about it, protons are all positively charged, but they're very close together. Now, if you remember from Coulomb's law, back when we talked about electricity, we found this relationship that the Coulomb electric force, is going to be a constant times the product of the 2 charges divided by r squared. When the 2 charges have the same sign, they're both positive when we're dealing with protons, then it's a repulsive force. And when r is really small, then the repulsion force F is really, really large. So these protons should be pushing away from each other, and the nuclei just shouldn't make sense. They shouldn't exist because these protons are always pushing away from each other. That's where the strong nuclear force comes in. When these protons are pushed closer together, it actually turns into this strong force, which binds all the protons and neutrons together. And we're dealing with very, very small distances. 10 to the minus 15th meters, you're talking like a femtometer, which is a millionth of a nanometer, or even less. Now, when you have large numbers of protons, you're going to need more neutrons to help with the strong force. That's what neutrons do, is they help with this strong force. And so we look at what's called the nuclear shell model, which is the number of nucleon quantum energy levels, the number of nucleons needed for this strong force to exist. You can have a stable nucleus if the total number of nucleons is one of these numbers, 2, 8, 20, 28, 50, 82, or 126. If the total number of nucleons, protons plus neutrons, equals that one of those numbers, you have a very stable nucleus. However, the more protons you have, the more neutrons you're going to need. Here is a chart showing that relationship. In this chart, you have the y-axis is the number of neutrons, the x-axis is the number of protons, and you see a blue diagonal line. That's the 1-to-1 ratio, meaning along that line you have the same number of protons as you have neutrons. Anything above that line you have more neutrons, anything below that line you have more protons. You can see with these lower numbers of protons that the number of neutrons is right around that 1-to-1 ratio, which you're talking about helium, hydrogen, boron, carbon, oxygen, all of those atoms. We're going to roughly have the same number of neutrons as we do protons. But as we start getting to the larger elements, such as iron, iodine, magnesium, those types of elements, you start getting into this region where there are more neutrons than there are protons. These extra neutrons are essential for the strong force to hold all those protons together. And the larger the elements go, the more neutrons you need in order to keep your nucleus stable. This purple region here is what we call the band of stability. If your nucleus is within that range, and you've got a fairly stable nucleus. But every once in a while, you'll get an atom that lies, say, perhaps right there. If that's the case, then it's an unstable nucleus and can very easily break apart and undergo radioactive decay. So, generalization from nuclear stability: if the atomic number is less than 83, you're generally stable. But if it's greater than 83, you're generally unstable. If your atomic number, or your nucleon number rather, becomes one of these numbers, 2, 8, 20, so on, then you have an added bit of stability to those atoms. Now, atoms also tend to do better when you have pairs of protons and neutrons. That is, if you have an even number of nucleons. If you have an odd number, then that means you have one extra proton or one extra neutron that can't be put into a pair. When that happens, you have less stability. Now, when we look at small atoms, what we see is 1-to-1 ratios in all of your isotopes are stable for atoms with up to 20 protons. If you have more than 20 protons, you're going to need more than one neutron to every proton. All right, let's look again at the three different types of radioactive decay. The first is alpha emission. We already hit on this a little bit. An alpha emission is basically the expulsion of enough nucleons to be a helium nucleus, to form a helium nucleus. So here's your helium nucleus, which is taken out of radon. And when that happens, your new element is 2 mass numbers lower. And let me say that again, make sure I got it right. The atomic number is 2 numbers lower. and the mass number is 4. Is 4 under. You drop by 4. And so here you started with radon, element 86. And if you look at a periodic table, it drops to element 84, which would be polonium, looking at a periodic table. Now, this helium, this is our alpha particle. The thing about alpha particles is they don't penetrate very deeply into other substances. A helium nucleus or an alpha particle, same thing, can be stopped by a simple piece of paper. Let's contrast that with a beta particle. When you have beta emission, basically what happens is you have an atom, for instance, we have carbon here, and then something happens in the nucleus. One neutron is turned into a proton, so your atomic number goes up, but your mass number stays the same. In this transition from a neutron to a proton, an electron is created, and so the electron is expelled away from the nucleus. This is your beta particle. So beta emission is one neutron turning into a proton, atomic number goes up by 1, but the mass number stays the same, and the result is the creation of an electron. Now, this type of radioactivity is far more penetrating. It would not be stopped by a piece of paper. In fact, this electron or beta particle would penetrate at least 1 centimeter into a brick of aluminum. So penetrates much further into materials. The third type of radioactive decay is gamma decay. This is the emission of high energy photons. Now, notice that the nucleus itself does not change. You start off with radon, it stays as radon. Atomic number, mass number all stay the same. It just emits this very high energy gamma wave, which is, of course, the highest energy electromagnetic wave we have, or that we know of. And this can penetrate far deeper than either of the other two. It can penetrate 5 centimeters or more into a brick of lead, which is very good at protecting from radioactive materials. But gamma rays can still penetrate 5 centimeters or more into lead. So here are some more generalizations. If you have more than 83 protons in an atom, we can generally expect alpha emission, which is the emission of a helium nucleus. The result is that your atom loses 2 protons and 2 neutrons. Now, if the condition is that the neutron to proton ratio is too large, we are above that band of stability we saw in the graph earlier. We tend to break down into what we call beta emission, the emission of an electron. You gain 1 proton, but there is no mass change. Gamma emission comes from having a nucleus that is too excited. There's too much energy within the nucleus. And the way it expels that energy is by emitting gamma rays. There's no change to the nucleus itself. Now here's one that is a little bit different that we haven't talked about yet. It's related to beta emission. Excuse me, there we go. It's related to beta emission. In this case, the neutron to proton ratio is too small. When that happens, instead of gaining a proton, you lose a proton. Notice the similarities here. You lose a proton turns into a neutron. So there's no change in mass. Now, this part you don't need to remember very well, just remember the idea. In order for this, remember that when we have a neutron turn into a proton, you emit an electron. Well, when you go backwards, you have a proton turning into a neutron, you emit the opposite of an electron, which is something that has the same mass as an electron, but has a positive charge. This is what we call a positron. These are far rarer in nature. You won't see them most of the time, and when they do exist, they often die out very quickly through processes I won't get into here. But it's pretty much the same thing as a beta emission, but dealing with a positron instead of an electron. This last one, you don't have to worry about so much. Just remember the alpha emission, beta emission, and gamma emission. These are the most critical ones for you to remember. Now, when we get back in the next videos, we'll talk about how we can actually use radioactive decay in things such as uranium for nuclear fission reactors, generation of electricity.